The previous video was about power series in general, and just to kind of review some of the stuff that you saw in that video and tie it together with this next section, 11.8, 11.9, and 11.10 are kind of a package, and so I just want to tie together 11.8 with 11.9, which we're going to do right now, and then also give you some idea about what 11.10 is going to entail. So in 11.8, you learned what an actual power series is, okay? And power series, they are just functions, okay? But they are functions that have some sort of a domain, and we refer to the domain of a power series as, we refer to the domain of a power series as the interval of convergence. And anytime you have an interval, it's always got a midway point. So its midway point is its center, centered at some a value, okay? And then to the left and right of that a value, you have some radius that gets you your interval of convergence. So r is the radius of convergence. So this may seem, kind of alien if you've never seen series before, but basically, if you have a power series, call it capital P of X, then P of some number, if you plug in just some number C, this is some sort of a series, right? And we know how to deal with these series from 11.2 through 11.6. More than likely, these series are going to end up falling into the category of either a geometric series or an alternating series, and we'll be able to discuss whether or not this number, P of C, converges or diverges. And if it converges, that means that that C value was inside of the interval of convergence. So if this series converges, that is equivalent to saying that the value C is in the interval of convergence for your power series, okay? And this P of C diverges is equivalent to saying that C is not inside the interval of convergence, which I'll write this way for our power series. Okay, so this is odd, but I just want to tie that together even with like 11.2 in the sense that we're just dealing with a function whose output is a series, and that won't necessarily be a finite value. You have to do some work to determine if the output is a finite value. If it is finite, if it converges, that value C is in the domain of the power series. Okay, so this was already alluded to in the 11.8 video, but the reason why we love power series is that sometimes power series represent weird functions. So I think the example that was given in 11.8 video was that cosine of x is actually a power series. Hopefully I get this right. I didn't stop to think about this before I started writing. Oh boy, here we go. All right, I think that's correct. So cosine of x is, and it's alternating. Okay, so I believe that's the power series for cosine of x. I guess if it's not, then good job that you can tell. But essentially, these weird functions like cosine, sine, e to the x, natural log of x, they have these power series representations, and that's really nice because power series are comprised of monomials. They're basically polynomials with an infinite degree. And that's super nice because we love using the power rule to differentiate and the reverse power rule to anti-differentiate. And so differentiating and anti-differentiating say anti-differentiating. Say this function. This function showed up on your 7.7 worksheet where we were using Simpson's rule to try to understand this function's antiderivative as an area, and we felt that even despite having all of these integration techniques, we could not integrate this function. We did not have a rule that would integrate e to the negative x squared. So for example, anti-differentiating e to the negative x squared will be able to do in the very first problem on this worksheet simply by anti-differentiating some polynomials of degree n. Okay, so that's the really nice part about power series as functions and vice versa. However, what we're going to do in this section is we're kind of just going to do some clever matching of weird functions with transformations, I'll say with transformations of common power series. And I'll show you what I mean on the next page. What I guess I mean here is to contrast with 11.10. In 11.10, instead of just kind of being clever and finding a nice common power series that we can manipulate to give us one of these weird functions, we're actually going to be able to explicitly build a power series. A power series for a function. Okay, from the ground up. We don't have to use any of our base power series. We're just going to start with a function and start building the power series term by term. Now, here's what I would like to really emphasize, because this is just a really tough section. I think anybody who has finished a degree in mathematics or even a master's or PhD in math would say that this is the hardest part of the entire calculus sequence, Calc 1, Calc 2, and Calc 3. You really want to try to understand these as deeply as possible so that you can utilize them in your, not just the rest of your degrees, but also in your careers, because they will not stop showing up. Okay, so here's what I want to make a quick note of. You might start with a function. One of the functions I mentioned above was e to the x squared. And well, what's the domain of that function? The domain of that function is everything. We don't have any issues plugging in a real number to e to the negative x squared. We get a finite output. Now, we can actually form a power series, and we're going to do that. We're going to form a power series for this function, and so we'll do that on page 1. But the power series has its own domain. It has its own interval of convergence, and I just want to make a really strong point here that the domain of the function compared to the domain of the power series, which is the interval of convergence, those are sometimes different. Sometimes they're the same, but sometimes they're different. Here's an example, because this is a function that we're also going to do in this worksheet. I believe this comes up on page 3. Well, what's the domain of arctan of x? The domain is everything, because the range of tangent is everything. So arctan has domain all real numbers. However, the power series that we're going to build for arctan is only valid between -1 and 1. And so these two intervals are not the same. And I just want to really drive that home, that the domain of your function is not the same as the interval of convergence for the power series that you identify with the function. All right, so that was my big spiel. Let's get to it. Here are the common functions, the common power series that we're going to use as our building blocks, mostly just for this section, because an 11.10 will actually be able to build these power series. So I'm just telling you to believe me, believe me, believe me, believe me, believe me, and we will actually construct these in 11.10. All right, so each of these power series represent a function. So that power series in the parentheses represents e to the x. And what's important to note is that e to the x has domain all real numbers, and its power series has an infinite interval of convergence, okay? So in fact, the domain of the function and the interval of convergence are the same. That doesn't have to happen. Here's another example. Here, this function, its domain is all real numbers except for at x equals 1, right? The interval of convergence for this function, what would that have to be? Well, we can see that that's a geometric series, and we know geometric series only converge if their common ratio is less than 1. This thing's common ratio is x. So this actually only converges for x values less than 1, while this guy's domain is all real numbers except for 1. Okay, and this is between -1 and 1. Okay, similarly, natural log of 1 plus x, that thing has domain all numbers where 1 plus x is bigger than 0. So anything between -1 and positive infinity, we're allowed to plug in for x here. However, the interval of convergence for this function is -1 to +1, including 1. And remember that the interval, I should say the radius of convergence, doesn't always tell you the whole story. Just because you know where the series is centered, this one's centered at 0, and it has radius of convergence equal to 1, but that means that you still need to check the endpoints of that interval, -1 to 1. And it turns out that this series does converge when x is 1, but it does not converge when x is -1. So that's just something to keep in mind, guys. There's a lot of subtlety here. Make sure you ask questions and you give yourself time to think about all of this. All right, here we go. So what we're going to do is we're going to start with a weird function, e to the -x squared. And we're going to create a power series for this weird function using one of our common functions power series. So e to the x, we already know from above, because I'm telling you and I've asked you to believe me for now. We'll build this in the next section. But e to the x can be expressed as a power series of this form. And if we write that as a power series, it's got coefficients 1 over n factorial, those would be your c sub n's, times x minus the center to the n power. So that is the power series for e to the x, and this is valid for any x value between -infinity and infinity. That's the radius of that's the interval of convergence. Now, e to the -x squared, well, that's just e to the x, where we've plugged in -x squared where we see an x. So that would be 1, because if you plug in -x squared for x into 1, you still get 1, plus -x squared instead of x, plus -x squared instead of x squared over 2 factorial, plus -x squared cubed over 3 factorial. And let's just simplify some of these terms so we see what's happening. This is 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial, and so on. So what's kind of different about e to the -x squared versus e to the positive x is that this power series is alternating. So we can write this instead as the sum from n equals 0 to infinity of the expression -1 to the n power, x to the 2n, because our exponents are all even, divided by n factorial. Okay, now I am not going to prove this to you, but it's always important when you write this equal sign, what do you mean equals? Okay, what do you mean equal? So for example, what if I have x plus 1 over x plus 1? Now, that looks like we should say this is equal to 1, right? But it's only equal to 1 where it's valid. So this is as long as x is not negative 1. So whenever we write e to the negative x squared equals a power series, we need to describe the interval of convergence where this is actually valid. So maybe I'll just ask you to trust me and you should check this, but check that the radius of convergence is infinity. And so your interval of convergence is 0 minus infinity to 0 plus infinity. And here you don't need to check the endpoints because the endpoints are positive and negative infinity. All right, let's keep going. Why is this useful? So this is going to answer this question. Why do we care? Why are we rewriting e to the negative x squared as this power series? Well, this is nice because if you'll recall, this problem that we tried to work on back in section 7.7 on Simpson's rule, this is hard. There actually aren't any good integration techniques to anti-differentiate e to the negative x squared. You can try substitution. That's not going to work. You can try by parts. That probably won't work either. So because this is such a hard question, what we can do instead is use its power series expression. So what this says is, let's use the first three non-zero terms of our power series. So our first three non-zero terms of our power series, I'm going to call it s sub 3 of x, okay, is 1 minus x squared plus x to the fourth over 2 factorial. And remember, 2 factorial is just 2 times 1, so that's 2. So instead of computing this integral, we're going to say, well, this is about equal to the integral from 0 to 1 of 1 minus x squared plus x to the fourth over 2. Because that polynomial, s sub 3, is starting to approximate e to the negative x squared. Well, we can just do the reverse power rule. That's the beauty of this, is instead of anti-differentiating e to the negative x squared, we're going to anti-differentiate using the reverse power rule. We get x minus x cubed over 3 plus x to the fifth over 5 times 2, which is 10, evaluated from 0 to 1. And this turns out to be 23 over 30. Okay. Excellent. And then the last question is, what is the maximum possible error in your approximation? Well, remember that because we are using an alternating series, what is the error for an alternating series? So what we're actually trying to approximate, oops, and that's not even the correct series, is it? So this series is the series for e to the negative x squared, but we're actually using its antiderivative. So its antiderivative, this equality, by the way, we have to be careful, but this equality is true by the theorem, the next theorem we're going to see. So this thing's antiderivative is actually the antiderivative of these little terms, which is, let's do n equals 0 to infinity, minus 1 to the n, and then if we raise the power of n by 1, we get x to the 2n plus 1, and then we need to divide, we already have an n factorial, but we need to divide by that new power. Okay, so that is the antiderivative. Maybe I should tack a little plus c on there to be good. That's the antiderivative for our power series. And this antiderivative is, as you can see, it is an alternating series. Maybe I'll write it one more time so it's in the form that we typically like to consider alternating series in. So if I increase n by 1, I subtract 1 from n. It's kind of like a translation in my series terms. So this becomes all over n factorial times 2n. All right, remember that the actual value of this, which we care about when x is 1, right? That's what we had to do to compute this little guy. The actual value of that alternating series when x is 1, let's call that s, that has to be within some error. Let me write what we computed here. That has to be within some error of our the next term in the sequence, which would be a sub 4, since we used 3 terms. And a sub 4 is, hi again. I mucked up a little example here. So when you anti-differentiate this, and I switched my limits on this, I switched my range for n. Everywhere you see an n, I should have replaced that n with n minus 1 in parentheses. And in doing so, if I had done that in parentheses, my powers here would actually end up being x to the 2n minus 1 and 2n minus 1. So that's my bad. So that makes this 2n minus 1 when n is 4. That would be 7. And in the denominator, we would have 2n minus 1 2n minus 1 times when n is 4, 2n minus 1 is 7. And this should be, oh my goodness, sorry everyone. This should be n minus 1 factorial. I was like, why is this so weird? So this is n minus 1 factorial, which makes this 3 factorial. All right, god dang it. So this is 3 factorial times 7, and 3 factorial is 6, times 7 is 42. Whew. Okay, all right. Thanks for playing along here. Let's keep going. So here's the theorem I mentioned in the previous page. The whole point of this, and this is what we just did in part B, we kind of used the theorem right here without having seen it yet. If you've got a power series and it has a positive radius of convergence, then your power series is differentiable. Why is it differentiable? Well, because it's made up of a bunch of polynomials. All right, polynomials are like our favorite thing ever because they're mega continuous and mega differentiable everywhere. So our power series is differentiable on its interval of convergence. All right, so whatever its interval of convergence is up here, a minus r to a plus r, it's differentiable on that interval as well. Furthermore, your power series can be integrated or differentiated term by term on the interval of convergence. And that's exactly what we just did on the previous problem. We integrated term by term of our series. And I want to just highlight here why we love this, because of the reverse or the normal power rule. We get to differentiate or anti-differentiate weird functions using reverse and normal power rule. So last thing is that if you have a power series centered at some number a for an antiderivative of p or the derivative of p, then that antiderivative or derivative also has the same radius of convergence. This just saves you time, all right? So let me go back up here. I said check that r is infinity, right? But this is fine. And in fact, this power series interval of convergence must also be minus infinity to infinity by the theorem, because it's the antiderivative of a power series with the same interval of convergence. Okay, here, this is fun. So now let's apply this theorem. We already applied the theorem to the anti-differentiating e to the negative x squared, but we can similarly apply the theorem by differentiating term by term. So we said that e to the minus x squared has a series expansion up here in the orange. So let me copy that. We've got the sum from n equals 0 to infinity of x to the 2n because our powers are even, divided by n factorial. So if we want to take the derivative of e to the minus x squared, that would be the same as taking the derivative of this infinite series. All right. I'm just going to tell you, and this is pretty technical, like this theorem is actually very powerful, but what this part of the theorem is giving us is it's allowing us to switch the sum and the derivative's place when the sum is infinite. We can do this no problem when you only have a finite number of things being added up and you want to take the derivative of those. But when you have an infinite number of things added up, there's all sorts of problems that could arise. So the fact that we can switch those orders of adding versus differentiating, it's a pretty big deal. So that's what the theorem is giving you. All right, and we're just going to take the derivative of each term, which we can do very easily because each term is just a power function, right? It's x to the 2n divided by n factorial. So the derivative of that little red cloud, if we use the power rule, we would have 2n coming down front. Oops. X, we need to reduce the power of the exponent by 1, and we're still all over n factorial. All right, so this says that the derivative of e to the minus x squared is, and again, these purple signs, we should probably say this is true for all x in this interval, and by the theorem, this equal sign will be true for all x in this interval, okay, is equal to the power series from n equals 0 to infinity of the series 2n times x to the 2n minus 1 power divided by n factorial. Okay, and I'm going to clean this up ever so slightly just so that we have something more interesting, I suppose. I'm going to write this as n equals 0 to infinity. I'm going to pull that 2 out to the back. Okay, so this little 2 is going to come to the back. And I'm also going to pull an x out. And if I pull an x out, how many x's am I left with? Well, I've got an n and I've lost an x, right? Okay, and downstairs we've got n factorial. And I'm going to do one more simplification regarding the n and the n factorial because n factorial has a factor of n in it. Oops. So this reduces to sum from n equals 0 to infinity. When that n in the numerator cancels with the n factorial in the denominator, you're left with n minus 1 factorial. And this 2x is just chilling out here to the side. Okay. Oh goodness, I messed up. I'm having a hard time today, guys. So I forgot that this is actually an alternating series, right? So this should have had a negative 1 to the n. This should have had, I'll just put it over here because it's constant, negative 1 to the n. This should have a little negative 1 to the n, a negative 1 to the n, and a negative 1 to the n. Okay, are we all right with that? I hope so. Okay, I'm going to do one last thing then. I'm going to steal a negative 1 and put it over with the 2x. And if I steal a negative 1 to the n, I'm left with negative 1 to the n minus 1 times the rest of my series, x to the 2n minus 2 all over n minus 1 factorial times a negative 2x. Okay, and then last but not least, because we've dragged a couple things over, the first couple terms here are going to be, oh no, we're fine. Okay, we're golden. Great, so this is hopefully looking familiar. This series right here is exactly what we said e to the negative x squared is. So that is e to the negative x squared times negative 2x. So obviously we can differentiate e to the negative x squared just using the chain rule. right? The derivative of a composition of functions is the derivative of the outside, leave the inside alone, times the derivative of the inside. So this is just trying to convince you that term by term differentiation is nothing to be scared of, I guess, if I may. So this all checks out, and this is, again, it's valid for all x values between negative infinity and infinity. Okay, example 3 is, to be honest, the other two examples are lovely, but they're pretty intense. This example hopefully serves to just be a simple, like, let's put all this together and review what we've been able to do. So this function, 1 over 1 minus 5x, we want to write it as a power series, some infinite sum from n equals 0 to infinity with some coefficients, c sub n, times x minus a to the nth power, okay? So how are we going to do this? Again, in 11.10, we'll freaking build this thing. No problem, we'll build it from the ground up. In this section, what we're going to instead do is we're going to use a common power series and make the appropriate transformation to that common series so that it fits the series that we're interested in. So notice that 1 over 1 minus 5x is just 1 over 1 minus x, where we've plugged 5x in, okay? And the infinite series for 1 over 1 minus x is up here. Okay, so that's the series we're going to use, 1 plus x squared plus x cubed plus x to the 4th, except everywhere we saw x, we're going to replace it with 5x. Okay, so 5x, 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 so on and so forth. Okay, now, here we go again. I've written equals, and what do we mean? What do we mean? So we need to test what the radius of convergence is so that we can find the interval of convergence for this, right? We also have to keep in mind what the domain of our original function is, because that matters as well. So the domain of our original function is any x value that's not 1 over 5, right? If you plug 1 over 5 in for x, you've got 0 in the denominator, and that's bad. However, there are no other values of x that would make this function undefined. So we can't have positive 1/5. As for the power series, this is a geometric series. Let's write it as such. So this is a power series with 5x as our common ratio to the n minus 1 power. So because our common ratio is 5x, we know that this converges only when the common ratio of 5x in magnitude is less than 1. And that means that we need 5x to be between -1 and 1. That would make its magnitude less than 1. And that means that x needs to be between -1/5 and positive 1/5. Okay, so that tells you that the center is at 0, the radius of convergence is -1/5 to positive 1/5. So this equal sign is valid only for x values in the interval -1/5 to positive 1/5. All right, I almost asked if there are any questions. Maybe you will have questions. All right. Great. So this next example, I made a little Desmos. I'll include the Desmos link in the YouTube video so that you guys can refer to it. But again, like, we're building a sequence of polynomials that get closer and closer and closer to approximating arctangent. And here's the thing, is that arctan of x, we will be able to explicitly build its power series expansion in 11.10. But right now, we don't have those tools. And so instead, we're going to use what we already know about arctan. And here's what I know about arctan. I know that it is the antiderivative of this lovely function 1 over 1 plus x squared dx. Okay. So because it's an antiderivative of 1 over 1 plus x squared, and 1 over 1 plus x squared is close enough to one of our common power series functions, we're essentially going to do what we did here in example 3. In fact, I kind of wish example 3 were just 1 over 1 plus x squared, but we're going to do exactly this idea. So let's find a power series expansion for 1 over 1 plus x squared because it kind of looks like 1 over 1 minus x. We have to do a little trickery to make it look like that, but there it is. So this looks like 1 over 1 minus negative x squared. So in the power series expansion for 1 over 1 minus x, we're going to replace x with a negative x squared. So this is 1 plus, this is the power series expansion for 1 over 1 minus just x. But everywhere I had x in the original series, I'm going to put my negative x squared there. Okay, and this goes on. All right. Now, sorry, I'm probably being super annoying about this, but I just can't stress it enough. What do I mean equals? What do I mean here? Okay. In fact, what's the domain of your original function? Are there any values for x where this is undefined? No, this thing's domain is all real numbers. There's no issue with what you can plug into x. Does that mean that the power series you find for it will always give you the right output for that function? No. So this thing has an interval of convergence. And what is its interval of convergence? Well, this series ends up looking like once we reduce it down, we end up getting, I believe it's alternating. Yeah, what do we get? Yeah, it's alternating. If we start at 1 and go to infinity, our first term will be negative 1 to the n minus 1, x to the 2 times n minus 1, because we've got even powers of x. All right, so this is an alternating series, and moreover, you can also think of it as a geometric series by just squishing the negative 1 in with the x. So it's geometric with, what do I want to say? This is, how do I want to write this? Sorry. 2n minus 2. Oh. Yeah, okay. So